We now explore how to implement subroutines at the assembly level.
We illustrate this with MIPS, where we have the $RA register to store the return address.
Since invoking a subroutine changes control twice, first from the caller to the callee, and on completion from the callee to the caller, we have two instructions. The JRL saves the return address, the address of the next instruction, in the dedicated register $RA, before jumping to the function.
JRL is the only MIPS instruction that can access the value of the program counter so that it can store the return address PC+4 in $RA.
To transfer control back to the callee must jump to address in register JR that was stored in $RA.
When the subroutine does not call other subroutines, it does not need to save the $RA register in the stack.
However, when the subroutine has parameters, the argument convention for registers applies.
The caller will set parameters in the A registers, starting with $0.
In the example here, we have a subroutine that prints the values of an array.
The first parameter is the pointer to the start of the array and is copied by the caller to $0.
The second parameter is the array's length, and the caller passes this parameter by copying the value to $1 before the JRL.
In this first example, there is no return value, but if the callee is a function returning a value, the V registers should be used.
Also, in this example, there are no further calls, but it is good practice in the subroutine to copy the parameters to variables or the stack.
That way, the A registers can be reused, as it would be here. The $0 register is used in system calls.
The subroutine must work on temporary variables, that is, T registers.
In this example, $T3 is used for the local index counter I.
The pointer to scan the array is $T1, while $T5 is used to calculate one less the size and decide if a comma or an end-of-line character follows printing an integer value.
If the subroutine were to use S registers, and not do all its work with T registers, then it must save the S registers it will use in the stack.
The subroutine must honor the convention not to affect S registers.
If the subroutine were to call another subroutine, then it is better to use S registers for any values required after the subroutine call.
Preserving S registers is crucial because the subroutine has no obligation to respect the T registers.
We illustrate this with the subroutine that sorts an array of numbers using a subroutine to find the largest value in an array and place it at the first position of the array.
We design the core of the subroutine sort using S registers.
We copy the first parameter and initialize a local variable named the tail in the $S1 register.
The $S2 register is for the second parameter, the size of the array.
The local variable current size is allocated to register $S3.
And the local variable I is placed in register $S4.
Thus, since sort will affect all these S registers, we must preserve their values when control arrives at the subroutine sort by shifting the stack pointer $SP.
Then, with the stack pointer as the base, we store $RA in the registers.
We can now write the code for leaving the subroutine.
We re-establish the values of the S registers before the call, by loading them from the stack, again using the stack pointer.
We finish by returning the stack pointer to its position when the subroutine was called.
If the sort subroutine did not use the stack to save the S registers, then the calling code that uses $S3 and $S1 after calling sort becomes incorrect.
Such a code assumes that calling sort leaves its S registers intact.
The body of the sort is a for loop, with variable I, in register $S4, as the enumerator.
The loop decreases the value of current size in each iteration by 1.
Also, the loop moves the pointer to the array by 4 units because it is an array of words.
Inside the loop is the call to subroutine max.
Note that after a call to subroutine max in sort, we use $S1, $S2, $S3, and $S4.
Therefore, subroutine max must preserve these values when it uses these S registers.
Max is recursive, it calls itself, so we must use S registers to ensure the recursive call can save the context of the current instance, guarantee preservation of values.
We copy the parameters into registers $S1 and $S2.
We test if the size is 1, which returns the value of the only element in the array.
When the array is larger than 1, we need an auxiliary local variable, a pointer, for the address of the tail of the array, all items except the first.
The parameters for the recursive call are set, in particular, the new size and the new pointer.
After the recursive call, we retrieve the result in register $V0.
This result must be compared with the value currently at the front of the array.
If the result of the recursive call is smaller, there is no need to swap. but we have a new returned value.
If we need to swap, we store the values in the correct order in the array.
Note that this is redundant, but we should always return a value in register $V0 when coding a function.
Since success registers are used, the code must save all these at the entry point of subroutine max and restore them from the stack at completion.